can start, Neeldhara.
Okay, yes. All right. Very good evening, everyone. As usual, warm welcome to the weekly live session. Thank you for joining us on a Saturday evening. I'll just make a couple of quick announcements before I hand it over to Arjun, who will, as usual, walk you through solutions for the programming assignments whose deadlines have passed, and maybe some hints for the ones that are currently ongoing. But basically, I think there were some snags with the links for week 6 material on the course website. All of those are now fixed, and you should also have the code from the lectures reflecting properly on the GitHub repository now. We are running a little bit behind our originally envisioned schedule, but you will see announcements regarding the materials for the upcoming weeks, very shortly over this weekend. So watch out for those. And I think up to week 4 for sure, you can find code in both C++ and Python. I think I just merged a pull request today for a Python version of the DSU implementation. I know some of you were looking for a Python version. There were inquiries about this in Discord. So I'm happy to say that there are Python versions for DSU now on the official repository. For the graph problems, I think we have basically been doing all the solutions in C++, but a lot of the implementations of the standard algorithms, let's say whether it's BFS, DFS, Dijkstra, Bellman-Ford, Floyd-Warshall, modified Dijkstra, where you use a priority queue instead of using this circus that we do with sets. All of these are actually also there in the GitHub repository for the competitive programming 4th edition book. And the repository is freely available. So you can actually look things up there where you will find versions not only in Python, but also in Java. So the only thing is, of course, it's not packaged in the context of the problems that we're working on, but really just, I think you'll find everything that you need. The crucial part of the logic of these algorithms is already there. And in terms of just porting it over and making it work for you in the context of a specific problem, that part is typically not too hard. So if you're worried about like just not seeing Python code or Java code or whatever, I think you should be able to find it from the CP book GitHub repository. And I think links to that are all over the place on the course website and elsewhere. So please do check that out. That would be my recommendation for the sections and graph algorithms. So up to week 4, I think we have at least C++ and Python, and sometimes also Java. And for weeks 5 and 6 so far, you'll find the code that you need also in the CP book GitHub repository. So I hope that helps. And yeah, I think that's pretty much all I had off the top of my head. So as usual, to everybody, especially who's joined us in Zoom, feel free to participate in the discussion either over chat or by just unmuting yourself whenever you'd like. And I see that there are some of you who are watching us on YouTube. You're welcome to hop on to Zoom if you like, or if you prefer to watch on YouTube, please post any questions or comments in the chat. And we'll be monitoring that as well. So we'll take it as we go along. So, all right. So Arjun, over to you. Do you want to discuss either the week 6? I think the week 7 materials are still have not been released. So, but the people are working on the week 6 programming assignment right now. And I think the week 5 solutions or the week 5 deadline is done with. And I think this was not the case in our last meeting. So week 5 was still ongoing. So we could either do solutions for week 5 or hints for week 6, or maybe both, depending on.
Yeah, I think we can do both. So maybe before that, do the people here have any particular questions which can be addressed? So yeah, I think the agenda is mainly to discuss week 5 problems and give some hints for week 6 assignment, programming assignments. Apart from this, is there any other question which others would like, any other questions which others would like to ask? You can just unmute and talk if you want to. Okay, so if not, let's start with, okay, maybe try. Yes, Ayush, I do have my board. I'm not sure if it'll work. Let's hope. Yes, that's exactly what I was trying to figure out just now. Neeldhara, how exactly do I share my whiteboard here? I'm a bit confused with the admin
I
control.
do believe that you are a co-host, so there should be sharing permissions. Can you see like a green share
Share
screen?
screen, yes.
Yeah, a thing at the
Oh
center.
yeah, okay. This does work. This does work. Yeah, yeah.
Yeah.
Okay, so can you see my
Yes.
whiteboard?
Yes,
Great.
I see your cursor and the lines. Yeah, perfect.
Okay. So let's just recap week 5 problem assignment 1. So it's a very short statement, so let me just read it aloud. You're given a rooted tree containing n nodes, which are numbered from 1 to n. Each node has a weight attached to it, which is given by wi. Your goal is to find a pair of nodes u, v, such that u is an ancestor of v, and wu minus wv is maximized. And you want to output this maximum difference possible. So what does it mean? So you're given some tree. So you're given a rooted tree. But note that in this statement, it doesn't say what the root is. But if you go down to the input, the input format is, some people might find this slightly weird. So if you're used to the usual format where you're given the edges as u, v, you see that this input format is different. In this input format, it's for every node, you're given the parent of its node, right? So for you're given P1 to Pm. Sorry, that's a typo. It should be Pn. Let me change that. So you're given P1 to Pn, where Pi represents the parent of node I. And in particular, if this parent is -1, then it is the root, right? So so let's just take some random rooted tree. Let's say this is 3, 5, 1, 2, and 4, right? So here P1 will be 3 because the parent of node 1 is 3. P4 will be 1. P5 will be 3. P2 will be 1. And P3 will be -1, right? Because 3 doesn't have any parent. So its parent is, we just, the notation we use is it's -1. And these are the inputs which are given to you, right? So using this, you have to, yeah, okay. Using this, you have to find out, you have to kind of build this tree and then do whatever they're asking, right? So this is also a very common method of inputting a tree without explicitly telling the edges. You're given the parent of each node. Yeah? So just be, it might be slightly non-trivial when you look at it first, but it's no different than the usual format. So cool. So in a lot of problems, you'll be explicitly told that root 1 is the node, but here it is not the case. The root could be any of the n nodes, and in particular, you need to go and check which I has pi equal to -1, and that I is the root, right? So let's do that first. So given that we have 3, 1, 3, 1, and -1, let us go over this array. Let's look at which is minus. There'll be exactly 1 -1, right? Because there's only one root in a tree. So you find this, and now you realize that, okay, it's P3 is the one which is -1. So my root is 3, right? And using these, how do I build my edges? So if P1 equal to 3, what does it mean? There is an edge between 1 and 3, right? Because parent of node 1 is 3, which means 3, 1 is a node. Sorry, is an edge. So if I know that this is an edge, I can do my usual stuff. So I have an adjacency list, and I'll push 3 into the adjacency list of 1, and I'll push 1 into the adjacency list of 3, right? Adjacents ADJ of 1 dot pushback of 3, and ADJ of 3 dot pushback of 1 is the typical thing you'll do when you have an adjacency list. So the only difference here being, because you're given it like this, if P of X equals Y, this means X comma Y is an edge. The only edge case is when Y equal to -1 in this case, this case, 3 comma minus 1 is obviously not an edge because it does not make sense. Right? So you just have to be careful of that edge case. Otherwise, the rest are all exactly what you would do otherwise in an adjacency list format. And you can build this tree. You can basically build the adjacency list, the array of vectors you build it. And once you've done it, you also know which the root is. So now you are ready to start the problem. So till now it was kind of like parsing the input, right? So now we have the structure, that is, it is a tree. We have all the edges, and we also know which the root is. Great. So now let's go back to the problem and think of what exactly is being asked. So the problem is basically saying, okay, so you're also given the W. So you'll have a W array as well, which is W1, W2 to Wn. And you have to look for a pair U comma V such that I think U is answer. Yeah, U should be an ancestor of V. So what is an ancestor? Ancestor of a node is just a node which is above V. It could be V itself, or it could be above V, right? Above, I mean, so no, like be mindful of the fact that terms like above, below, ancestor, descendant makes sense only in a rooted tree. In an unrooted tree, there is no concept of above and below because there is no orientation. Like I can flip the tree upside down and things will still be the same. It's still the same tree, but now above becomes below and below becomes above. So never use the terms above, below. Similarly, subtree as well. Subtree in a different setting would make sense, but in our usual tree subtree, it does not make sense. So whenever you see these terms, that is, you should be very sure that it's a rooted tree, and if it's explicit that there is a rooted tree, maybe there's some implicit condition which makes it a rooted tree, and you have to think about that first. But anyway, so here we know that it's a rooted tree. So we have ancestors and descendants, and so we need to find a pair U comma V such that U is an ancestor of V, and WU minus WV, right? This is the value that we want to maximize. So how do we do this? So I think one natural way is to just look at all pairs of U comma V, right? So how many pairs are there? There are NC2, like n square pairs, right? And for each of these pairs, we can ask, okay, is U an ancestor of V? If it is not, just directly check it. If it is an ancestor, then okay, I'll compute WU minus WV, and amongst all these, I find the maximum. So now then the question becomes, how do I know that one vertex is an ancestor of another vertex or not? And this, there are multiple solutions. So for one way you could do is like start from V and just keep going up. So in the adjacency list, like apart from the adjacency list, you can also have a parent list, which in this case is exactly given to you, right? So this parent array is something which you already have. So I can go to 2. Who is the parent of 2? It's P2, which is 1, right? Then I go to 1, and who is the parent of 1? It's P1, which is 3, right? So from 2, I keep going up the chain till I reach the root. And along this way, I check whether I ever hit U or not. If I ever hit a U, then okay, U is an ancestor of V. If I never hit a U, then U is not an ancestor of V, right? So this is a method to check whether U is an ancestor of V. But of course, this takes just this checking takes linear time, order n time. And why is that? Because if the tree is, say, just a huge line, then to check whether something is an ancestor of this, I have to keep going up all the way up, which takes like n time, right? So just checking whether U is an ancestor of V could take n time. And of course, we are going over all pairs of U comma V, which is n square. So the total approach, this is like order of n cube, right? So in order of n cube, this approach should work. And let's look at the constraints. Subtask 1 gives us 500. And what is 500 cube? It's 125 into 10 power 6, which is 1.25 into 10 power 8. So, oops, sorry. Yeah. So 1.25 into 10 power 8 should probably pass. With some, I mean, it almost definitely passes, right? So that is like subtask 1. You might have to make some small, depending on people, you might have to make some small optimization, but I'm fairly certain it just directly passes. But if you look at the original constraints, n is 10 power 4, and 10 power 4 cube is 10 power 12, which is way beyond our way beyond the time limit that we can afford. So we definitely need something much better. And the note here, I think I mentioned in last class, was don't just solve this for 10 power 4. So if it's 10 power 4, then an order n square solution is going to work. But we don't just want an order n squared solution. We want something better than it. In particular, we want an order n solution. And here it's the constraints are reduced just because uploading larger files is hard. So we gave 10 power 4. But this problem can actually be solved for much larger n as well. So now let's look at how to optimize this. So this kind of keeps coming up in multiple places. Okay, maybe let me just check the chat once. Okay, that's nothing. Great. So please interrupt if something isn't clear. Yeah. So as I was saying, so now the question is, how do we optimize this n cube? So one way to do is to optimize the time in which you find out whether u is an ancestor of v or not. So here we spent order n time. This can actually be done in constant time with some pre-computation. Okay, so let's talk about that. So what is the question? The question is, given a tree and given queries of the form u, v, you want to find whether u is an ancestor of v or not. This brings us to something called Dfs numbers, which most of you should be familiar with. If you've seen Dfs, then hopefully when you read the theory of Dfs, you also came across this term called Dfs number, or entry time and exit time, right? So it's basically as follows. So if I have a node like this, I'm not labeling them, something like this, and you start a DFS from this node. So okay, let me label them as well, just to be 1, 2, 3, 4, 5, and 6. So if I start a DFS from 1, I enter this node at this. So basically think of running a DFS on this tree while a clock is running, right? So I have a clock here. It is initially t equal to, say, 0. The time is 0. And after each move, my time increments by 1, right? So I enter this node at time t equal to 0, okay? And after that, what do? I go to one of its neighbors. Say I go to this neighbor, right? So now I'm entering this node so now at this point, time has incremented and become 1. So I've entered at time equal to 1, right? Then again, from here, I go to one of its neighbors. Let's say I go here. So now time has become 2. So I've entered at time equal to 2, right? And now there is no other neighbor. So the only neighbor here has already been visited. So I won't visit it again. So I go back up. So the time I leave, so let's say while doing this also time increases by 1. So the time at which I leave this is at time t equal to 3, right? Then at time t equal to 4, I come to this node again. Then I go to its next neighbor, which is this. So it's 3, then 4, then at time t equal to 5, I reach this node. So the first time I enter this node is at time t equal to 5. Then at time t equal to 6, I leave it. Then I come here, time t equal to 7. I've done all its neighbors, so I go up. So I'm exiting this thing at time t equal to 7. Then I come at t equal to 8. Here 9. Here 10. Then I leave at 11. Then I come here. Then I leave this at 12. Then I come here and I leave this at 13. Right? So these are the numbers 0, 13. is the entry and exit time of node 1. 1, 7 is the entry and exit time of node 2. 2, 3, similarly 5, 6. There are various ways of implementing this. I mean, but almost all of them work. So I'm just giving whatever comes to my mind right now. 10, 11. Yeah. So these are basically what we call, sorry about that. Yeah. So these are what we call entry and exit times of every node while performing a DFS. It can also be called as a DFS number. Lots of names for these things. Now the major, there are various properties related to this, but the property that we are really interested in right now is basically the fact that this range is contained within this range. That is 5, 6 is contained within 1, 7, and 1, 7 is contained within 0, 13. Similarly, 10, 11 is contained within 9 to 12. So think of these as ranges, right? So 9, 12 is basically the time is the entire time I spend in the subtree of this node. I entered this at 9, I exited at 12, right? So similarly here, I entered at 1, I exited this whole thing at 7. So everything inside is between 1 and 7, right? So 5, 6 has to be within 1 and 7, 2, 3 has to be within 1 and 7. So now this obviously gives us a simple way to check for ancestor, right? So if u's time is enter u and exit u, oops, sorry, exit u, yeah. And similarly, look at entry of v and exit of v. Then if u is an ancestor of v, then what should happen? This should be within this range. In particular, it should mean that entry of u should be less than entry of v, and exit of u should be greater than exit of v. Yeah. So this case is kind of clear to see, right? That is, if u is an ancestor of v, then I should have entered u before I entered v, and I can exit u only after I exit v. This much should be pretty clear. What is maybe slightly more surprising is that this is an if and only if condition. That is, if this condition is satisfied, this means that u is definitely an ancestor of v. And why is that? That is also clear if you think of it a bit, because v can't be outside the subtree of u, because I started after I started u, but I finished before I finished v. I started after I started u, but I finished before I finished u. That means I'm still inside the subtree of u, right? And so v is a descendant of u, so u is an ancestor of v, right? So basically these 2 points, if both these are satisfied, then u is an ancestor of v, and this will be satisfied if u is ancestor. It's an if and only if condition. So now this can be checked in just constant time. So what do? We just run one DFS at the very beginning. We compute the entry and exit times for all nodes. And now for each of the u comma v, we go through all u comma v. Then we check if u is an ancestor of v or not by doing this check in constant time. And if it is an ancestor, then only among those values we pick the maximum of wu minus wv, and we output this maximum, right? So this now optimizes the n cube that we had to order n square. Like there's some initial n to do DFS, so it's n plus n square. That's still just n square, right? So now we've gotten to order of n square, right? An order of n square for 10 power 4 will pass. So in NPTEL, you will get a full score, but this is not the intended solution. The intended solution is even faster, right? So for n equal to 10 power 5 or even n equal to 10 power 6, you should be able to solve it. And now the question is, how do you do that, right? So now let's go one step further and try to do it. And before that, let me see if there are any doubts. No, I don't see any. Just give me a second. Okay. So now we want to do the same problem, but we want to be a lot more efficient. In particular, we want it to be in order n. So how do you go about doing that? Yeah. So this is where the hint that I had given comes to the picture. So the hint I had given was something along the lines of, okay, I want to compute, or rather I want the maximum of WU minus WV. But instead of looking at all the ends, so okay, so going with the thought process. So what was the very first step in the algo that we had till now? It was looking at all pairs of U comma V. But right then and there at the very first step lies our problem, right? We can't look at all pairs because that is bound to be n square, but we want to do something much better than n square, right? And what do we do in such cases? Kind of like we want to coalesce a lot of options into one option, right? So even though there are actually n square options, um, we don't want to look at each and every single option because that takes too much time. So we want to be kind of smart in it, right? So if we have this huge bag, yeah, so let's call this the solution space. Oops, my spelling is bad. Solution space. Yeah, so solution space basically has all U comma V thrown into it, all the possible optimal solutions, right? So there are like NC2, not even NC2, yeah, something like NC2 pairs thrown into this bag. But that's so we can't go and look at each and every one of them and then find the maximum. So we want to be smarter, right? So one thing we could do is, one optimization we could think of is, okay, we're looking at all U comma V and then checking whether it's a ancestor or not, and then doing this. What if instead I could somehow directly go to only those pairs which are ancestor comma descendants? If that is a small enough number, and if somehow I'm able to do it, able to get to them in constant time, then my life might become easier. But then that's a very nice line of thought, but then you quickly see that even that does not work, because just again, as the previous example, just take a line graph, right? So say the vertices are 1, 2, 3 up till n, and here you see that the number of ancestor comma descendant pairs is still order n square. That is, if this is an ancestor, I have n minus 1 choices for descendants. If I take 2 to be the ancestor, I have n minus 2 choices for descendants, and so on and so forth. So you see it comes down to 1. So sum of all this is n minus 1 into n by 2, which is like order s n square. Yeah. So you actually have order of n square valid possible optimal solutions, right? So which is still bad for us because it's still n square and we can't afford to do that. So this line of thought also kind of abruptly ends. So it's not, so the issue is not with that. So this issue is even more kind of fundamental in some sense, and we need to take care of that. So what do we do? The point being, whenever you have something like a function of f of x comma y, right? There's a function which depends on 2 parameters, and I want to maximize this, right? So one kind of general approach to take is to try and fix one of the parameters, right? So if x is fixed to be x0, right? Now amongst these, what is the maximum I can get for all values of y, right? Then I'll fix x to be the other value, x1. Now, amongst all values of y, what is the maximum I can get? So I'll take max amongst all of this, max amongst all of this. Then I'll fix x to be x2. Say there are n different possible values that x can take. So I'll look at all those n values. I'll fix x to be each of those values. And once I fixed x, I'll run through all values of y and I'll find what the maximum is. and take it. And now I'll take the max amongst all of these guys, right? If I just do this naively, it's not going to save any time because there are n possibilities, and say there are m possibilities for y, it's going to end up taking n into m time, which is no worse, no better than just simply going and looking at all pairs of x comma, because there are n into m such pairs. But the kind of the optimization usually comes from this part. Like if I fix x, do I actually need to run over all y and then find the best possible y, or can I do something smart about it, right? Can I have some observation which tells me directly that, okay, what should that y be such that f of x1 comma y is maximized, right? If both my parameters are variable, I didn't know what to do. But if one of my parameters is fixed, then can I kind of efficiently find out what value y should take for f of x1 comma y to be maximum, right? And that's kind of what we're going to do. So if I can do this in constant time, right? So then the whole thing just becomes order n, right? From order n now, it's dropped drastically to just order n, and that's a huge thing. In other words, in another perspective, in the solution space perspective, what we're kind of doing is we are dividing the solution space into n sub bags, where in each sub bag, I'm fixing a particular value of x, and I have various y. And amongst all this, I find the maximum. Amongst all these, I find the maximum. Amongst all these, I find the maximum. And I take the maximum amongst all these sub bags, and then I output the answer. Right? That's basically the overall picture. And coming to the actual problem, we have, so my f of xy is wu minus wv, right? I want to maximize this value, right? So let's take the tree again. 1, 2, 3, 4. Say this is the tree we have. And say I want to maximize this. So I'm going to run through all values that you can take. How many values can you take? You can take 7 values. You can be any of these 7 values, right? And for each of them, I'm going to find the best v. So let's say u is fixed to be 4, right? So I want to find the max value that w4 minus wv can take over all valid choices of v. So what are all the valid choices of v? U is the ancestor, right? So if this is u, then v has to be this, or this, right? So v has 4 options. Now, amongst these 4 options, I want to find which is the v which maximizes w4 minus wv. But now, see, max of 2 plus x is just the same as 2 plus max of x, right? I can take constants out. So w4 here is a constant, right? That's kind of what has happened by fixing wu. So I can take w4 outside. So it becomes w4 minus, sorry. So if I take w4 outside, then what happens? I want to maximize w4 minus wv. So if I take out w4 outside, I want to maximize minus wv. What does that mean? That's same as just minimizing wv, right? Because what is maximum of a negative value? It's as small as possible, right? Okay, I should explain this better. Maybe not algebraically. Let's say 5 minus some x. If I want to maximize this, I should minimize x, right? It's as simple as that. So all I need to do is find the minimum wv, and I'll subtract that minimum wv from w4, and that should give me this max, right? So now all I need to do is in this subtree, which has the minimum weight, and whatever that minimum weight is, I'll subtract that from w4, and that is going to be my answer for this particular sub bag. And I'm going to do this for each and every u. and I'm going to take the max amongst all of this, right? This is the whole point. Now, how do I compute these? This is where DFS comes into the picture. Let's say we have min subtree of u is the array that we are maintaining, where min subtree of u contains the smallest weight in the subtree of u, right? So now I'm going to do DFS. When I come to a leaf, there is nothing beneath me, right? So what is the min subtree of u? It is my weight itself, right? There's nothing else, no other choice. So when I come to a leaf, I'm forced to just say min subtree of leaf equal to my weight itself, my own w leaf. So this is, let's say this is kind of fixed, this is fixed, and this is fixed. When I come here, when I come to 6, I have one child. So the min subtree of 6 is minimum of my own weight, comma, the weight in this subtree, which is min subtree of 7. Right? So it's min of w6, comma, min subtree of 7. Right? So that I can compute, and I get min subtree of 6. Then I've computed this. So min subtree of 4 now becomes min of my own weight, minimum in this subtree and minimum in this subtree. But these are already computed. Right? So I just take the min of this, this, and this, and I'm done again. Right? So in general, what we are basically doing is min subtree of u is minimum of my own weight and say I have some 3 children. Min subtree of I'm shortening min subtree to ms, so it's ms of c1, comma, ms of c2, comma, ms of c3. This is ms of u, and I store it in ms of u. And because I'm doing DFS, I'm guaranteed that I've finished these guys. So I've computed these values. So ms of c1, ms of c2, and ms of c3 are already found and written in the array. And so when I'm exiting u, at that point, I'll calculate ms of u and I'll store it. And I keep doing this for every node. And so in just order n time, whenever I'm doing my DFS, right then I compute these things. This is my usual DFS computation, right? So we compute this, and finally I have my ms of the root as well. And now what do? We just go over all values of u and look at w of wu minus ms of u, okay? Because ms of u tells us the minimum. Okay, at some point I think I said maximum by mistake. I always meant minimum. Yeah. Okay, maybe I didn't make a mistake. So ms of u tells me the minimum value in my subtree. So I just subtract that from wu, and I take the max of this value amongst all u, and I output that. So this whole thing can be done in order of n time. So does that make sense? Any questions?
I actually accidentally closed the YouTube page. Do you have it open, Arjun? I don't know if anyone.
Yes, 1 second. There are no comments there. Let me just send the link in.
Yeah, I kind of assumed at some point that everybody who was following along joined us here. So yeah.
Yeah. Cool. So let's then move on to the second problem of of week 4. Let me read it once. Give me a second. Okay. So you're given an n cross m grid in which some cells are blocked. Okay. So I think we've spent a lot of time in the first room, so I'll be a bit quicker on the second one. So you're given n cross m grid. Some of the cells are blocked. You're also given R1 and R2. You initially place 2 coins A comma B on the cells 1 comma 1 and 1 comma M. That is the leftmost and the rightmost cells of the first row, topmost row. In each turn, you first pick A. Suppose it's at x1 comma y1. Then you can move it to any cell x2 y2, which is one. The first constraint is that x2 y2 should not be blocked. And the second constraint is that x2 y2 should be at a Manhattan distance of not more than r1. Right. So this Manhattan distance we had discussed last time. So it's the difference between the x coordinates, absolute difference between the x coordinates, and the absolute difference between the y coordinates should be at most r1. So you can do this. Then you pick B from its current cell, say x3, y3, and you do the same thing. But now the Manhattan distance is not capped at R1, rather it's capped at R2, right? So and you keep repeating. So this first A then B is called, I think, one step. It's called one turn, right? And your goal is to get both A and B to the same cell. After the end of a round, you want both A and B to be in the same cell. And the objective is to, the second objective is to minimize the number of turns needed. Right? If there are many ways to get A and B to the same cell, what is the minimum number of turns you need to get them to the same cell? Constraints are actually not that large. Even the excluding the subtask, even the very first, even the general constraint itself are that n and m are less than equal to 100. Just give me 1 second. Sorry about that. Yeah. So you want so the constraints of the grid is pretty small. So how do you go about doing this? Let's first look at the first subtask. R1 equal to R2 equal to 1. That is at both for both the cells, for both the coins, you can move them kind of at most 1 Manhattan distance, right? So either you can be at the same cell, right? Because the Manhattan distance of the cell with yourself is this 0, or you can go in one of the 4 cardinal directions. You can go up, down, left, or right. Like notice that you can't go diagonally, because if you go diagonally 1 step, its Manhattan distance is 2, right? Because the x coordinate differs by 1 and y coordinate differs by 1. So you can only go in one of the 4 cardinal directions. So how do you solve this? So I think I frankly don't remember what exactly the clue it was that I had given. Okay, I think I'd given a fair amount of the approach. So okay, so when you have 2 such, okay, I think the first line of thought is that this is very clearly a graph problem, where each cell is a vertex and you have some edges. We don't know what exactly these edges are, and it's something to do with shortest paths, right? But of course the hurdle is that there are 2 people moving and not just 1 person, so you need to be a bit careful about that. But I hope the first intuition that it's a graph should be clear enough. So now let's look at what exactly the graph is. As we said, the vertices are the n into m cells, right? And what are the edges? The edges are whatever you can transition from one cell in one turn. should be an edge, right? So if I'm at 5,5 and I can go to, I don't know, 10,11, then that should be an edge from 5,5 to 10,11. One nice thing is that this is an undirected graph, because if I can go from one cell to other graph to another cell, I can come from the other cell to this cell as well, right? Because first of all, both of them have to be unblocked, otherwise I won't add the edge at all. It's kind of meaningless. And Manhattan distance is symmetric, right? If I swap x1, x2, that is, instead of x1 minus x2, I do x2 minus x1, it's the same because it's an absolute value. So because Manhattan distance is symmetric, this graph is undirected. I don't need to worry about directed edges. All these edges are undirected, right? So I can just build this graph at the very beginning, right? So I have, what are the number of edges? It's n into m, which is 10 power 4. And so the number of edges is at most 10 power 8, right? Which is kind of bad, but let's go with it. Why is 10 power 8 bad? 10 power 8 is bad because time-wise, it's probably fine. But memory-wise, it's pretty bad, right? I can't store 10 power 8. Which is where the next constraint comes in very handy, which is the fact that R1 and R2 are at most 10, right? So why does this help us? So if R1 comma R2 is less than equal to 10, and I'm at a cell X comma Y, I can go up at most 10. I can go here at most 10, right? 10 and 10. And I'm not going to spend too much time on this. So it's you just think about a bit. You'll see that sorry, I'm messing this up too badly. Sorry. Let me draw a bit. Yeah. So if I'm at X comma Y, I can go up 10. I can go down 10, right 10, and left 10. That is, all these cells are reachable in Manhattan distance at most 10. All these cells are reachable in Manhattan distance at most 10. This cell is not reachable because its Manhattan distance is 10 plus 1, which is 11. But this is reachable. Why? It's 9 plus 1, 10, which is less equal 10. Similarly, this is not reachable because it's 9 plus 2, which is 11. But this is reachable, which is 8, sorry. Yeah, 8 plus 2, just 10, right? So you see that this is the reachability graph. So everything inside this triangle, I can reach. Similarly, everything in this I can reach. Here I can reach, and here I can reach. So it's kind of like a diamond, or like a tilted, a square tilted by 90 degrees. But this isn't very relevant for us. What is relevant is that if my Manhattan distance is 10, then the number of cells I can reach is at most 10. So here it's 10, right? So in this whole row, it's like 20. Here it's, or let's just take 10. 10 in this triangle, it's 10, 9, 8 up till 1, which is like 10 square, right? And it's repeated like 4 times. So it's very roughly 4 into 10 square. It's less than that, but it's very, very, very roughly this, right? So if my Manhattan distance is 10, then the number of cells that are reachable from one cell is at most 400, right? So the number of edges adjacent to a single vertex is at most 400. And so if my number of vertices is only 100 into 100, which is 10 power 4, and the number of edges adjacent to any cell is at most 400, the total number of edges is then 400 into 10 power 4, which is 4 into 10 power 6. And this is well within our limits, right? So m is less than equal to 4 into 10 power 6, which is good for us. 10 power 8 is bad, but 4 to 10 power 6 is fine, right? Because 4 to 10 power 6 is only like a few MBs, like a cup, like probably like, I forget it, what is it, like 12, 16 MB or something like that, right? So that is well within our limits. So one thing I can do is just literally make this graph. I have a graph with what are the variables? I forget. A graph with n into m vertices, and all these edges, the edges are not too large, so are not too many, so I can make all these edges. And now let's get to the actual problem, which is I have two vertices in this graph, and I want them to reach, I mean, at each step, at each turn, the A goes one step, takes one edge, B takes another edge, and so on and so forth until they meet, right? So how would you do this? One simple thing is just find the shortest path between A and B, right? If the shortest path is 10, then in 5 steps they can meet, right? Does that make sense? Yeah, but this is assuming that R1 is equal to R2, R1 is equal to R2, right? Because I'm kind of assuming symmetry, but that's not actually the case, right? R1 might not be equal to R2, in which case we actually need two graphs to do something like this, and then it kind of becomes a bit convoluted. So instead, we'll change our approach a bit more differently. But I hope you got this point. If R1 is equal to R2, then just this one graph is enough, right? I can go between anything and so on and so forth. So I just find the shortest path between A and B, and that by 2 ceiling of that, probably ceiling of that should give me my answer. But now we have this extra complication that R1 might not be equal to R2, right? So here we take a slight deviation and say, okay, let's build two different graphs, right? In the first graph, the edges are according to R1, and in the second graph, the edges are according to R2. Now, let's run a BFS from A on the graph corresponding to R1, which I'm just calling R1, right? So what does this mean? If I start from A1, if I start from A, the initial point where cell A was, coin A was, then to reach any particular cell, how many turns does it need? For A, forgetting B, just A, how many turns does it need to get to, 13, 15? That I can find easily, right? By just doing a simple BFS on this graph. Notice that it's just a BFS, not even a Dijkstra. It's just a BFS because all these edges are just one turn each, right? So it's just BFS. Similarly, I do a BFS on the graph corresponding to R2, but now I start from the starting cell of coin B, right? So start from B on the graph corresponding to R2, and I compute the shortest distance from B to every other cell. Now, if A and B have to finally meet at some cell, say that cell is X, Y, right? Then how many steps did it take to get from A to here for A? It is whatever this distance the BFS told me on this. Similarly, what was it for B? It's whatever this gave for this, right? So distance of X, Y in this graph plus distance of X, Y on this graph is the distance, the total distance traveled by A and B, right? But both of these are done simultaneously, right? It's not that A does then B does. One turn is A doing, B doing. This is counted as one turn. So what do I want? I want an X, Y such that the maximum distance amongst, say A took 10 steps to go to X, Y, and B took only 7 steps. So then after how many steps will I reach it? I'll reach it after 10 steps, right? Because A will take 10 steps to get there. B will take only 7, but then he'll stay at 7. B will come there and just stay there, right? So, but eventually 10 is what matters because it's at the 10th timestamp that both of them will actually meet. So the 7 is kind of irrelevant for us, right? So if for any X, Y, I look at dist 1 of X, Y, which is the distance in this graph, and dist 2 of X, which is the distance in this, and I'll take the maximum of these two, right? And this maximum should be as small as possible, right? So all I'm going to do is I'm going to do min of max of dist1 of x comma y comma dist2 of x comma y. Yeah. So I just go over all xy, which is n into m, which is only 10 power 4. So that's fine. I know the distance, number of steps it takes for A to get there. I know the number of steps it takes for B to get there, right? Amongst these two, what is the max? Which is the maximum? Is this greater than this or this greater than this? Whichever it is, I take that value. And that value I want to minimize. So I minimize this over all x comma y. And whatever the final answer is, that is what I output. Yeah. So that covers this entire problem. I know I went a bit fast, but I hope that clears any doubt you had. Please ping if something isn't clear.
So I think Amit had a question.
Where was it?
Oh, in the Zoom chat. He's asking, can one participant move more than one step consecutively?
Wait, why can't I see it? Wait. Oh, I'm not getting notifications for the chat for some reason.
Okay, yeah, right.
Okay.
Not
One
sure.
sec. Let me see the chat. Can one participant move more than one step? No, they can't, Amit. So it is A, then B, then A, then B. But what can be done is that because staying at the same cell is allowed, right? Because the Manhattan distance of a cell to itself is 0, which is less than equal to R1 and R2 always. So it can be A moves, then B just stays there, then A moves, then B can just stay there, and so on and so forth. That is definitely allowed. Does that answer the question? Great. Okay. So then I think let's move on to this week's questions. And let me try to give some brief hints. So the weeks, by this week I mean week 6. Week 6 was basically revolving around MST, minimum spanning trees.
Sorry, I think that was week 7, or that is going to be week 7.
Oh, sorry.
I had an assignment also for shortest paths. I think Dijkstra and Berman 4.
Okay. My bad. Yes. Yeah. Sorry. Yes. Yeah. So week 6 is the extra. So let me just look at problem 1. Alice, Bob, and Charlie live in a country where there are n cities. Cities are numbered. There is a flight from U to V, and you're given. Okay, so the costs are given in an adjacency matrix. Right. So A is Alice is in city A, Bob is in city B, and Charlie is in city C. And the question is, if Alice goes directly to Charlie's from A, you go directly to C, or if you go to B and then to C. Sorry, not directly. Sorry, I should not say directly. Without any constraints, you go from A to C, or you go with the constraint that you definitely have to pass through B to get to C. The question is, how much extra money do you have to spend because of that extra constraint, right? So this is the question. So this kind of just boils it down to 2 separate questions, which is, what is the minimum cost to go from A to C, and what is the minimum cost to go from A to B, and what is the minimum cost to go from B to C? And then you just do minimum cost of A to B plus minimum cost of B to C, and subtract it from, and from that you subtract minimum cost from A to C, and that gives you the extra cost that you have to spend, right? So all it boils down to is just literally shortest distance between 2 vertices, right? So you're given the matrix at the very beginning, you're given the adjacency matrix at the very beginning, and then you have a lot of queries, and each query is basically some number of shortest distance queries, right? So this is almost a fairly straightforward implementation of all pair shortest path, right? So APSP, all pair shortest path, is exactly this, right? So you do some pre-computation such that after the pre-computation, you can answer the shortest distance between any two vertices in constant time. And you'll see that that is exactly what is needed in the question, right? So that's the hint. The hint is all pair shortest path, and breaking down the given question into, like, I think 3 different all pair shortest path queries, which should make life pretty easy. Okay.
Arjun, are there like multiple queries for like A, B, and C? I mean, I was wondering.
Yes, yes,
Okay.
yes.
Yeah, I just wanted to be sure that.
Yeah, so each of the next M line contains 3 integers ABC, which represent the this thing. Maybe did I not mention that in the actual statement?
No, I'm sure you.
Yeah, there are many scenarios given in which the initial cities are different. Yeah.
Right. Yeah,
which is why you need to do the pre-computation part as well.
Correct. Like if these were all like separate test cases, I mean, I guess, yeah, I think one of the things I've hopefully mentioned in the videos is that you have to watch out for the constraints when doing APSP in terms of the sizes of the graphs involved. So I'm assuming that, for example, if it was the same problem, but you didn't have to process a number of queries at once, let's say it was just one query per test case, then something like Dijkstra would have done the job for you, right? Sorry, did I lose your audio? Just 1 second. Okay, I think Arjun probably got disconnected as far as I can tell. Maybe we'll just wait for him to join us back. Yeah, so I'll just reiterate the point that I was making, which is that if you can see that from the constraints that your graph is rather small, that's already a hint that you can use APSP, and that's probably what is required from the problem as well. Okay, so while we are waiting for Arjun to rejoin us, are there any other questions, either from the week 6 assignments or from even the lectures of week 6, any of the materials? Happy to address them. Just take a look at stream once to be sure. Okay, so I think Arjun will be joining us back in a minute, so we'll just wait for some time.
Hello.
Hey, welcome back.
Sorry. I didn't notice that my laptop was not being charged.
Oh, okay, no worries.
Sorry, you were saying something when I got.
Yeah, I think I was just saying that, I mean, sometimes looking at the constraints can already give you a hint about whether, for instance, if it's a small graph, then at least you know that APSP is feasible. And depending on the problem, it may actually be required. On the other hand, if the graph was too big for APSP, and let's say that the queries were like you didn't have multiple queries. So suppose the problem was just that you're given A, B, and C, and you need to figure out exactly what you said you have to figure out. And these were all separate test cases. Then even Dijkstra would have been enough, is what I was saying.
Definitely. Yeah, I think you've nailed it.
Yeah. That's that was one. Yeah, because you have multiple queries on the same graph, then I think, then the APSP is the more.
And with different sources at each time. So
Correct.
You can't just have one Dijkstra or one BFS.
Correct.
we go on for all the shortest path.
Yeah, that makes sense.
Great. Okay, so let's move on to the second question. So sorry if someone had written something in the chat which I missed. Please just copy paste it again. So for now, I'll move on to question 2. So in program assignment 2, we are given a string s of length n. Each character is a digit. You have to start from s1, that is the beginning of the string, and you have to reach the end of the string. And to do so, you can make multiple teleports. Sorry. So from a particular si, you can either teleport to the value, or rather the index just before it or the index just after it, or you can teleport to any other index such that the values are the same. That is, if I'm at the 10th position, the 10th position is s10, the character value is say 7, then I can either go to s9 and s11 or s11, or I can go to any other index which has a 7 in it, whose value is 7, right? These are the different teleports that I can make. And the question, of course, is to find the minimum number of teleports to go from S1 to Sn, right? Okay, so this is, at least for some constraints, this is should hopefully be a pretty straightforward implementation of just BFS. You basically build a graph. So think of what the graph should be. What should be the vertices? What should be the edges? It's pretty similar to the previous problem that we saw, where the vertices are the n different indices, and the edges are basically, can I go from index u to index v in one teleport? If so, there is an edge between u and v. And here again, it's as similar to the previous problem, not the previous problem, the problem before that. It is an undirected graph. That is, if I can go from u to v, I can also go from v to u, right? Because they just look at all the 3 types of edges that you have, and you'll see that each of them is symmetric in some sense. Yeah. So that should lead to a fairly clear reduction to BFS. So you start from one vertex, you want to reach another vertex, you have all the edges, and how do you go there, right? But now then the complication arises when you go for slightly larger n. I think it starts from, say, subtask 4, where n is say 10 power 4. Still, theoretically, it's still the same, but the issue is with the number of edges that we have, right? And the number of edges can become pretty large. Why is that? Because if, say, all the vertices or all the indices have the same value, say all of them are 1, 1, 1, 1, 1, then what are the number of edges that we need to add? We need to add n choose 2 edges, right? Because from anything you can go to anything else because of the last category of teleporting when the values are the same, right? And this is a problem because even for n is 10 power 4, the number of edges is like 10 power 4 square, it's 10 power 8. And I possibly can't store all of them, right? So this becomes the main bottleneck that you have to try and overcome. The hint is that the approach is still the same. You still kind of just do a BFS, but you kind of don't add all these edges. Instead, try to come up with a graph where the number of edges is smaller, but the answer still remains the same. You might want to go into weighted graphs and do a Dijkstra. That makes life easier, So maybe I'll just give that as a hint. The hint is that at least one approach to this is to consider a different graph where the vertices are the same, but the edges are somewhat different. Actually, vertices, it can be the same or it can be slightly larger. I'll leave that up to you. It's more or less the same. Let's just say it's more or less the same. But the edges you have to basically make it. Sorry, sorry about that. The edges you have to make it such that number of edges reduces drastically. We don't want like n square edges. We want like order of n edges, right? And the trick is basically to add some weights to the edges. In particular, add the weight 0 and 1. Some edges will have weight 0. Some edges will have weight 1. Okay. Such that the shortest distance remains the same. So try to think of this, and hopefully that should get you to the final answer. Yeah. Cool. I think that's basically the hint for the second problem. So I'll stop here. If there are any particular questions, feel free to ask.
Okay, looks like we don't have any follow-up questions here. I hope everybody found that useful. I think, yeah, I don't see anything on YouTube either.
Amit has a question. Can I submit code for week 5 problems as practice? I believe so, right?
Yeah, I think I had this question from somebody in the second week after the first set of deadlines got over, and what I remember is that the answer from NPTEL was yes, it should be possible to submit as practice, but please check it out. I think there should be a natural way to do it. We don't really, I think we should probably just create some student logins for ourselves and, be able to test this for you. But for now, I'll just suggest Amit, just try it out. And if it doesn't work, then please let us know. But I believe you should be able to. So certainly if you submit something, if you are able to submit something for an assignment whose deadline is passed, then it will not affect your grade for better or worse. So I think the evaluations have been frozen. So you can just go ahead and try things out now. I think you should be fine. Okay, so all right. It does not work in the sense that there is no facility to submit at all, or that you try to submit and you don't get a response. Could you just elaborate on, like when you go to the assignment page, I'm sure the pages are still accessible. What happens?
Ma'am, there is no option of resubmitting like as a practice. I'm just seeing a large test case and my previous submission.
I see. Okay. My recollection is that the response I got was that it should be possible. Perhaps what we can do, I'm not sure, we can try this out offline. Arjun, maybe we can try to duplicate these assignments and make them available as a practice set. I'm sure that should be possible.
Yeah.
And I think we can do that. Okay. So I guess you can still see the assignments, but you cannot actually submit them. Fine. So that's a good point. We'll try to take care of that aspect of it for sure. Don't know if there was anything else. And if not, I suppose we could possibly wind this down here. We are a little bit over the hours. So thanks for sticking around till the very end. And we will be back next week. And of course, we continue to be available on Discord, so please feel free to ping us there. We can continue the conversation there if there was anything that did not get addressed during the live session. Or if you're watching this later, then please swing by Discord if you have anything to discuss. Cool. All right. So thanks very much, everyone. We'll just wish you all a very good night and a happy weekend for now. Bye, and thanks for joining us.
Thank you. Bye.